So there are symmetric matrices that we can solve by Cholesky decomposition. And let's define the symmetric matrix first. And actually we have defined this before, but let's remember here. A symmetric matrix has aij terms are equivalent to aji terms for all I and j, which means that the A matrix is equivalent to its transpose matrix. And basically these aij and aji are the terms on the matrix, in the matrix, below the diagonal and above the diagonal. So basically we have the diagonal and the terms below it and above it will be the same for the same terms actually. So if we have such a symmetric matrix, then we can use Cholesky decomposition method to be able to solve this. This is the most popular solution approach. And basically we can decompose a symmetric matrix into L and L transpose. As you can see here, this is similar to LU decomposition, but because we have a symmetric matrix, we have L and L transpose as the decomposition of the A matrix. So the resulting factors are the transposes of each other, basically. These are the transposes of each other. And the terms of the decomposition can be multiplied out and set equal to each other. So the terms means the terms of these. And for the kth row of the matrix, basically to be able to get this, the terms of L's are these LKI and LKK. And these are obtained by using these equations. As you can see here, the A terms in the A matrix and L terms in the L matrices divided by L term. Here also A matrix, the diagonal actually here, and here the diagonal of L's as well. And here the other values of L. And here K is the row, as you can see, here kth row of the L matrices. And I is going from 1 to K minus 1. So that's why I is different. And also J is the columns of the L matrices. And we can actually create a pseudocode to be able to write this as a MATLAB code, for instance. We have a for loop here for K for this from 1 to N. And we have another for loop for I. So this is the number of rows actually, N is the number of rows, and I is 1 minus K, 1 comma K minus 1. So whatever K here is, here it is minus 1. And we also have a summation term here. This summation term helps us to be able to sum Aij and Akj, as you can see here. And here another for loop for J, I from I to I minus 1. And in here we obtain AKI as AKI minus summation divided by AII. This is basically this equation is here. And we will finish this for loop. Also for this one, we will have another for loop to be able to get this summation as well. And from there, we will have this value here is here. You can see AKK and LKJ is the summation. This sum is this value. So because of the sum, we will have no negative term issue. And also this is true for the matrices which are positive definite, meaning that the X transpose times A times X is greater than 0. Also pivoting is not required to be able to solve this symmetric matrix when we use this pseudocode. And this is an advantage of this Cholesky decomposition. We will solve an example 11.2, to show the Cholesky decomposition application. For this matrix, you can see here, this is a symmetric matrix because for the upper and lower values of diagonal, you can see there's symmetry. 15 is here, 55 is here, 225 is here, and these are the diagonals. So this is symmetric. When you fold it, you can see that each term matches to the other term. So if this is symmetric, then we can say we can use the Cholesky decomposition. Then, of course, we will use our equations, which were, maybe we can write them here quickly. LKI is equivalent to AKI minus summation I minus 1 j equals 1 Lij Lkj divided by Lii. And also the other one, Lkk, let's keep this in mind and then continue. Akk k minus 1 summation j equals 1 Lkj square. When you have these, you will easily solve the Cholesky decomposition, apply the Cholesky decomposition actually. So for the first row, for this one, we can skip this equation and just continue with the second equation. So let's write here, maybe with blue. For the first row, use Lkk equation. Only the second equation is enough. And for this, we will have first L11. So when k is 1, L11 is equivalent to, in root square, Akk is A11 minus, here this is minus, so minus here, in summation k minus 1 means 0, j equals 1, and L 1 square. So this is goes from j1 to 0, meaning that actually this term doesn't exist. So here we have to be careful. If j is equals, if it says j is starting from 1, but this is lower than j equals 1, so this goes 0 because the top is 0. Then it is just A11, meaning that A11 is 6 here, you can see. So it is root 6, which gives us 2.4495. Okay, so we use this for k equals 1. Now we can go to the second row actually. So simply because the Cholesky decomposition will give us an L matrix, which is just a lower triangle. In the first row, we will only have one term, and it is this term, because this is a 3 by 3 matrix. Basically, we will have just this lower, and we will have only one term here. But if it was larger than 3 by 3, then we will use the LKI term as well over here to be able to solve the other terms as well. But for this one, we don't need to use that. We only use LKK equation. But in the second one, we will have two terms in the second row. So in the second row, we will use also the other equation as well. But let's start with LKK for that too. For the second row, use LKK and LKI equations. So let's start with LKK, but because we already completed k equals 1, we will continue with k equals 2. Then L22 is equivalent to this equation here, A22 minus summation, k is 1 now, j equals 1. So because this is from 1 to 1, this can be used as L21 square. Actually, summation just gives this term to us, nothing else. So the summation disappears, actually only this one, L21 square. Then this is equivalent to A22 is basically this 55 minus L21 is actually this value because we already found this. No, actually this is L11. We will need to find L21 using this equation, LKI. So let's use that. For the same k equals 2, we will calculate L21 using the first equation. In the first equation, we have a 2 I equals 1, a21 minus the summation is I minus 1. I is actually here 1. So I here it becomes 0 and j starts from 1, meaning that this term is again 0 actually. This becomes 0 divided by L II. Lii means L11. So this L11 we already found this value. Now we will use them. So A21 is 15 here. Divided by L11, we found here already L11, 2.4495, and the result here is 6.1237. So then we will use this here, 6.1237. Then this becomes L22 becomes 4.1833. So maybe it's better to use this before find this, then use this L22. First use this, then use this in the second row. So we obtain this as well. I will write the L. Actually, we will need to go to I equals 1, also I equals 2. But for that, we need to go to third row because in the second row, we only have I equals 1 because I goes from 1 to k minus 1. So k is 2. That means it goes to up to 1 only. So this stays here for second row. For the third row, we will calculate the other one, the other terms, the third terms actually, 3 terms. So up to this point, let's write the L matrix here to see the terms. So first of all, we found L11, which is 2.4495. The rest is 0 actually. And for the second row, we found L21, which is 6.1237 here. And also, we found the second term of this, L22 here, 4.1833. So this is a lower triangle matrix, it will be. The third term here is 0, this is 0, this is 0. And finally, the last term, the third term, will have 3 terms, so that it will have a lower triangle. So let's find them as well. And for that, for the third row, again we will use the first and second equation. So only for the first row we will use the second equation, but for the rest we will use both equations. For the third row we have k equals 3. K equals 3. Then with this we will start with I equals 1, and also we will continue with I equals 2 because it's up to k minus 1, which is 2. If I equals 1, then let's start with the first equation here. L31 is equivalent to A31 minus summation I is 0 again and j equals 1. So this is 0. I will not write that. It goes to 0 and L11, which gives us A31 is 55 in our matrix. You can see these ones. Actually, yeah, we can say this. 31 divided by L11, we already found it as 2.4495. Then the result here is 22.454. So this becomes L31, and we can write it here as 22.454. So let's continue to the on the right side here, maybe. Now we did I equals 1. Now let's work on I equals 2. And of course k equals 3. And the same equation, L32 is equivalent to A32 minus, and summation is now 1, j equals 1. So we will only have Lij. Ij means actually I was 2 and j is 1, L21, and also Lkj. Lkj is L, k is 3, j is 1. So this value divided by Lii here, and that's I was 2, so L22. If we write these, L32 is equivalent to A32 is basically 225 minus, so summation is only one value because it's j is from 1 to 1, and that's why it's just L21, L31. We can write them here. L21 is 6.1237 times L31 is 22.454 divided by L22 is 4.1833. So you can get these L values from here, basically. Then L32 is equivalent to 20.917. We can write it here. L32 means here 20.917. So for the diagonal term, for this term, now we will use the second equation, this one. Let's use it. L33 is equivalent to root square A33 minus k minus 1 to 2 from j equals 1 L3j square. So this L3j becomes, actually, let's write it here, A33 minus L31 plus L32, and there is minus in the beginning, so it's minus L32. Let's write these down. L33 is equivalent to A33 is 979 root square, of course, minus L31. You can see now L31 is this, L32 is this. Let's write them down. Of course, the square of these. Here we forgot about the square, because in the equation here we have square. Square of this and square of this. So 22.454 square minus 20.917 square. So L33 becomes, from here if we calculate, 6.1101. So here 6.1101. As you can see, we calculated this L, and now A becomes L times, actually L times L transpose. You can just get the transpose of this, meaning that these terms will be upper triangles, and multiply them. It will give us A. So that's simple, actually, to be able to get the Cholesky decomposition. This is a simple example to show Cholesky decomposition. You can apply it in other examples as well now, because you now learned about how to use these.